At Fermilab, we study nature at its most fundamental, drilling down to the smallest scales of matter using some of the largest and most advanced machines in the world. Accelerators, powerful microscopes, send particles barreling at near light speed into other matter, creating subatomic scraps. Detectors zoom in on those fleeting pieces, making the invisible perceptible. And sophisticated computers sweep through all of it, crushing mountains of information into gems of data. We also use our cutting-edge technology to explore the mysteries of dark matter and the quantum realm. Thousands of scientists from around the world partner with Fermilab to explore how the universe works, expanding humanity's understanding of matter, energy, space, and time. Fermilab is solving the mysteries of the universe.
Hello, and thank you so much for joining us this afternoon. I hope you've had a wonderful time at the Fermilab Open House so far, and that you will join us for some of our other events later today. It is my pleasure to introduce a man who needs no introduction, but is about to get one anyway, Jerry Zimmer, Zimmerman, aka Mr. Freeze. Jerry has been bringing the wonders of cryogenics to the community for the past 22 years, delighting tens of thousands of adults and students alike. After a 2-year hiatus, he is back here today to do his live show streamed to you live from the Ramsey Auditorium. I know that all of you are very excited to see our perennial favorite, and we are excited to welcome him back. And so with that, please give a silent, though hopefully large round of applause to the coolest man I know, Mr. Freeze.
A bit about me. As she said, my real name is not Mr. Freeze. It's actually Jerry Zimmerman, and I am a physicist here at Fermilab. Now, Fermilab is a national lab. You've been part of the virtual open house we've been doing. And the Fermilab, being a national lab, has lots of different technologies, sciences we have to use. And one of the areas in particular that we use a lot is this, cryogenics. Now, kids, cryogenics is not the science of crying, but it is the science of the extreme cold. Thus my name, Mr. Freeze, nickname Mr. Freeze. But before I begin, I always like to be sure to show you exactly what I'm working with. I have the same material in both these containers, and it's something we use a lot of here at Fermilab. This is liquid nitrogen. That's it. It's just a clear liquid. In fact, if you didn't know better, you could actually very easily mistake that stuff for water. Now, there's a few things that we notice right off the bat that do seem a little different. First of all, what's this stuff coming off here? Well, it's fog. It's water vapor condensed out of the air because the liquid in the bag is so cold that it's condensing that water vapor out. What's happening to the liquid in the bag? It's bubbling. It's bubbling because it's boiling. It's boiling because everything's so hot to it that everything makes it boil. My glove is so hot to that liquid that my glove makes that liquid boil. Just like an electric iron makes water boil, my glove makes that. Now, one of the things I usually like to do during my show is I like to see if you can guess how cold do you think it really is. So how cold do you think it is? Well, it's so cold, it makes a snowman shiver. Okay, it doesn't really make a snowman shiver, but we can see how cold it is by taking and putting a little of the liquid nitrogen on my thermometer here, and we can measure what temperature that liquid is really at. So liquid nitrogen is about 45 degrees. No, that's not right. How cold? It's actually minus 320 degrees Fahrenheit. That's how cold this liquid is. And because it is so cold, it has a very powerful effect on lots of things. Now, one of the first things that we noticed was the liquid was boiling. Now, when you boil water, you get steam. This isn't water, this is nitrogen. So what am I going to get when I boil nitrogen? Well, nitrogen gas, or basically air. So I put a little in the bag, seal the bag up. What will happen is that bag will fill with nitrogen gas caused by that liquid expanding, inflating that bag just like a, oh, Okay. Well, I guess this bag really wasn't big enough for this demonstration. I'm probably going to need a bigger bag here. Oh, one of the things that's kind of interesting is we're always interested in cryogenics. How much does it expand? Well, the way to find out how much it expands is if you take a given amount of liquid, and in this case, we'll use a cup of liquid, and you put it in a container that can hold it, like this bag, and we'll see how much gas you get from just one cup of liquid. So you take 1 cup of liquid, you put it in the bag, you seal the bag up, and you'll see how much gas you get from each 1 cup of liquid. Now, there's a good sized bag, lots of cups of gas. You can kind of make the table as a hot plate, warming that liquid up inside the bag, expanding it. And now the question is this bag going to be big enough to hold what? No. So what do you do when you have a little scientific setback? Do you give up? Do you quit? No. You buy a bigger bag. So now I have a bigger bag, and I can repeat my experiment by taking 1 cup of liquid, putting it in the bag, sealing the bag up, and seeing how much this bag can hold. And now the question, of course, is this bag going to be big enough to hold that liquid converted to gas? Now, it's a much bigger bag. In fact, this bag is, in fact, a 55-gallon trash bag. So that's a lot of cups of gas. But is that going to be enough to hold 1 cup of liquid converted into gas? And the answer is yes. In fact, this bag is just big enough to hold 1 cup of converted gas. For actual numbers, for each 1 cup of nitrogen, I get 700 cups of gas. By the way, 55 gallons is actually 720 cups. So this bag is, in fact, just big enough to hold that 1 cup converted gas. Now, why doesn't that float? By the way, this is nitrogen, not helium. So it isn't lighter than air. It is just air. Now, that's fine. But the truth is, it'd be much easier if I actually had a container I could hold it in. Now, because I am kind of the clumsy sort, always make sure that I put a cork on this so I don't spill any of it. So what happens in that case? Oh, that's what happens. Okay. Well, the reason why that cork popped off is because the gas inside pressurized the bottle enough to force the cork off. There's actually a neat way to demonstrate another principle of science. If it's I kind of turn things around a little bit and do it this way. What? The reason why that bottle flew away, because it is just like a rocket engine in that case, because the gas pressure inside exhausting out the back makes the bottle fly away in the opposite direction. But the truth is, we probably still wouldn't do it that way. What we'd probably do is this. What happens in this case? The bottle blows up. Yeah, because the gas into the liquid inside causes so much pressure that the bottle would explode. Well, why am I standing here holding it if I know the bottle's going to blow up? One of the things about working in cryogenics is you have to understand the hazards and how to handle it safely. In this case, how do we prevent this bottle from blowing up? I poke a hole in the lid. At the end of the demonstration, we'll actually detonate one of these bottles and see how powerful it really is. It is quite dramatic. By the way, the containers up here have loose lids, so they can't build up pressure and cause an explosion. That's the only safe way to handle cryogenics, especially liquid nitrogen. Now, we've investigated the gas expanding, very interesting, but now we're going to investigate what happens when you introduce a gas into it. What's going to happen to a balloon? We'll put in here, see what happens. Well, this is kind of interesting. Yeah, it's going to change color. Oh, no, wait a second. It changed. Wait, is this? No, that's not it. Okay, is it, no, okay, how about, no, that, okay, wait, there seems to be a problem. No, that's not it either. What, It's got to be in here someplace. Oh, there it is. Okay. The air inside those balloons collapses 700 times the expansion ratio of liquidation, converted into a liquid, collapsing down in the bay. Once you bring it around, the air inside re-expands, occasionally does some of the fell, re-expand, re-inflating the balloons to the same shape and size were before I put them in. That's the reason why all these balloons were able to fit inside the container. By the way, just out of kind of a curious note, a while back here at Fermilab, I actually worked on an experiment. And the name of that experiment, and this is the truth, was called the dark side. So I was working for the dark side. Now, I wasn't actually in the movie. I was just working on an experiment called Dark Side. By the way, if you want to Google that, you need to Google Dark Side 50 because you'll never find it otherwise. But when I was asked to join that experiment, I was told it's going to take long hours, some weekends. And I said, okay, if I join your experiment, what do I get out of it? You know what they said? They said they're going to give me a lightsaber. I was expecting something other than a very, very light saber. By the way, I don't think these are very dangerous. I don't imagine anybody could get hurt by this lightsaber. But I also have here, which is one of my favorite pets. And even though you might think this is a puppy dog, it's really a chili dog. So we've investigated, what about a more rigid container? What about a regular bottle with a regular cap? Similar to the balloon, it collapses. What about an even more rigid container? I'll set that down there, it's going to fall over. I have here an empty can of pop with the top sealed with tape. So now, similarly, now one of the things kind of interesting about this is what happened to the balloon when I brought it back up. It reinflated, came back just the way it was before I put it in there. Aluminum can, the plastic bottle I'll do first. Warm it up with my hands here a little bit. Plastic bottle, there we go. Comes back. What about the can? The can does not. There's a reason for that. Some materials, like the aluminum of this can, actually get changed by the cryogenic temperature. It's actually called cryo treatment. Very standard in the machine industry nowadays to cryo treat different metals. In this case, because the aluminum is stronger, it would take more air to force it back out to its original shape. So if you ever see something on a product saying cryo treated, that's basically what they did, is they dipped it in liquidation to make it stronger for that application. You'll notice when I'm working up here that sometimes it looks like I'm reaching in these containers, and I can actually see where the liquid level is inside containers. And I have different things for different jobs. I have these blue gloves. They're very good for handling cryogenics. Not very good for putting your hand in, but they're good for handling very, very cold things. I have the tongs, which are very good for taking balloons like in and out of liquidation. But I also have these other gloves. Now this black glove here should be perfect for working at cryogenics, because this black glove is actually guaranteed liquid type. So no liquid can get through this glove onto my hand. So like this glove is perfect for me to, like, reach in and grab something. Is this a bad idea? What's going to happen is my fingers just going to bust up. Oh, no, I didn't actually lose any fingers. But this glove isn't very good to work at cryogenics because this glove itself changes into something that's in fact much more like glass. In fact, why do you think I'm wearing this white glove? Because of the cold temperatures? No, because if I did that with glass, what would happen to my hand? Yeah, I'd cut my hand. Do you know how hard it is to explain to people how you cut your hand on a rubber glove? Now, once this glove material warms back up, it actually regains its flexible nature. So it returns to the flexible nature it was before. So it's not permanently affected, but when it's at cryogenic temperature, it's very brittle. Now, we've investigated how certain materials are affected by this. One of the things that we do a lot of here at Fermilab, and the reason why we use cryogenics a lot, is because it is very good at keeping things cold. Some of the cryogenics we use, like liquid argon, are going to be used in very large detectors that we're building here at Fermilab. But one of the areas that a lot of people that don't realize how much cryogenics is used is that's actually used a lot in the food industry. One of the examples, McDonald's uses liquid nitrogen to freeze hamburger. So if you're ever wondering why it looks the way it does, why would they do that? Well, I can kind of demonstrate that a couple of ways. First of all, it's very cheap stuff. It actually only costs like 20 cents a gallon for liquid nitrogen. Secondly, it is just nitrogen like air, so it can't contaminate the food or damage the food. And the third reason I can demonstrate this way. I'm going to take and put some water in this bag. And now I'm going to add some liquid nitrogen. Now I have in this bag 2 liquids. One liquid is boiling while one liquid is freezing. And as you can see, the nitrogen is on top boiling while the water is on the bottom freezing. But as you see, it is causing the water to freeze very quickly. And this is the part that McDonald's Corporation likes. It basically freezes instantly. There's no time for any contamination to build up in the food because it is frozen so quickly. Now, this ice I am making here is regular water ice. Very odd shape because of the way it was formed. But also has a property, if you get a little smaller piece, that this ice is so cold. There we go. Yeah. Whoops, here we go. There we go. You get a smaller piece here. There we go. Yeah. This ice is so cold, it freezes to my skin. It's so far below 32 that it freezes to me before I melt it. Same idea as sticking your tongue to a flagpole in winter. Don't do that. It's very dangerous. Your tongue will stick to it, so don't do that. But this ice is so cold that it will actually freeze to my skin. So what would happen if I were to try to eat that ice? Would that be very good? No, that'd freeze to my tongue, be very painful. So what in the world would I be thinking of with a marshmallow? Obviously don't have a campfire up here, so I have to use the next best thing, which is of course liquid nitrogen. So now the question is, what do you do with a very well frozen marshmallow? Now, some people have suggested I make s'mores, but s'mores are supposed to be mushy, and this is no longer mushy, it's now crunchy. So now the question is, what do you do with crunchy marshmallows? It's not make Lucky Charms. I'm really not sure what those things are, but actually, if you don't mind, I'm a little thirsty, so don't mind, I'm gonna have just a little stack here. Oop. I'm sorry, I should not be smoking for you. Oh, that wasn't smoking, that was fogging. What happened there? The marshmallow's so cold, it is condensing the water vapor out of my breath, just like you see when you go outside in winter, same effect. Only this is caused by the marshmallow being so cold as to cause that fog. Now, like I said, we use a lot of liquid nitrogen here at Fermilab. By the way, those big trucks you see going down the highway, each one of those trucks holds 7,000 gallons. We actually use 2 of those trucks every single day. And like I said, McDonald's uses even more than we do. But why do we use so much liquid nitrogen? Well, I can demonstrate that a couple of ways. First thing, I have here an electromagnetic coil, and this is to demonstrate what was called the Lenz's law, L-E-N-Z law, Lenz's law. And Lenz's law says that when you put a conductor, like this aluminum ring, into a changing magnetic field, that produces a current in the conductor, and that current causes the magnetic field in the conductor that is opposed to the one it's in. So in this case, when I activate the coil, well, that's pretty neat. But what if we wanted to make this a better electrical conductor? Well, how do we do that? By doing this. By cryogenically freezing it, when it is cold, that aluminum will become a much better electrical conductor. And because it is a better electrical conductor, it will make a higher current. And that higher current will make a stronger magnetic field. And in this case, when I put this cold coil into the same magnetic field as I was at before, it goes much higher. And the reason it's going higher, because it is producing a higher current. What if I let this sit out and warm up a little bit? What would happen? Well, it actually wouldn't go as high, because the warmer it is, the poorer the conductor it is. It doesn't stay permanently a higher conductor. Only when it's cold is it a better electrical conductor. Now that's good, but the truth is here at Fermilab, we just don't want better electrical conductors. We actually want perfect electrical conductors. And how do we do that? Well, there's by churning some materials into extremely cold temperature, they actually become perfect electrical conductors. Now I have here a special track. And this track is special in that the track is actually made out of extremely powerful magnets. And it's to demonstrate a property we use a lot of here at Fermilab. And that property is what we call superconductivity. Now in this can, I have some special material. Now most superconductors actually don't operate to minus 450 degrees, but a few very special ones actually operate at minus 320 degrees, this temperature. Now in this can is some of that special high temperature superconductor. Now right now, this can has no magnetic properties at all, but I put a little spacer in there, my cardboard there, and I take liquid nitrogen and put it in my little can to let it cool down. Now you might be wondering, why is the cardboard there? It's not to protect the magnets or that from getting liquid nitrogen on. No, that cardboard is what is the space between the superconducting magnet I'm making by cooling down the car and the magnetic track. And that's the gap I want it to maintain. I want it to keep us that far away from the track at all times. Now, once this gets fully cold, and it'll take a minute here to cool all the way down. Grab my glove here. Yeah. Now this can will become a superconductor, the material, and as it does so, it doesn't want to get any closer to the magnet, doesn't want to move any farther away. It's called the Meissner effect. And in this case, what happens is, oops, not quite there, pretty close though. Just a little more nitrogen will get us there. Now that little car will not want to touch the track. It just want to ride on top of the track. Or in this case, keep that main space right there. And go back on here a little bit. There we go. I can kind of hear it as the nitrogen finally gets to the fully cold temperature. There we go. Now that little car is floating on that magnetic field because it is just cold enough to become a superconductor. And that superconductor doesn't want to get any closer to the track, but it also doesn't want to get any further away from the track. And I can demonstrate that by doing this. It'll actually float upside down as well as float right side up. That's because it doesn't want to get any closer to the magnet, doesn't want to get any further away from the magnet. It's keeping exactly that gap, that cardboard gap, while it's running around the track. So that's one of the main reasons we at Fermilab use cryogenics, is to make our materials superconducting. Now, if, by the way, I don't know if you know for sure, but you can ask questions. We'll have people pouring those questions to me so I can answer those questions at the end of the demonstration or as we go along. So feel free to ask questions of my demonstration as we go along. So right now we're going to do a little experiment. Now I have here a tennis ball and a racquetball. We're going to do a little background to our demonstration. And this tennis ball and this racquetball actually have an interesting thing. If you listen very carefully, racquetball, not that much. Tennis ball, that popping sound you heard was actually thunder. Thunder, how could that be thunder? What thunder is a sonic boom caused by air expanding faster than the speed of sound. In case of a lightning bolt, it's the heat of the lightning bolt causes that rapid expansion. In this case, the cloth covering the tennis ball caused the nitrogen expand so fast as to exceed the speed of sound expansion, causing a sonic boom, which you hear as thunder. Now, I do this as kind of a background demonstration, but it's kind of interesting anyway. If you're ever wondering why certain sports aren't really big in certain parts of the world, this is a good example. Racquetball in Alaska, not a good idea. Probably heard a lot of that. The Alaska Open, not one of those big tour events on the old tennis circuit anytime soon. Hit by that, you probably, actually in Alaska, they don't call it tennis. You actually call it dodgeball. So we do that as kind of a background demonstration. And whenever you're doing a science experiment, what you're actually trying to do is answer a question. So in our case, our question is, what do you think is going to happen to this ball? Now, before you do your experiment, you come up with your hypothesis, your educated guess. In our case, we could look at similar examples. We did a balloon. What happened to the balloon? It collapsed and came back. Okay. We did a racquetball and tennis ball. What happened to them? Oh, they got hard. So what do you think is going to happen to this ball? Is it going to collapse like the balloon or get hard like a racquetball tennis ball? So, well, we will find out. By doing the experiment, we'll see what we think. Now, the reason why the balloon collapsed was the air inside the balloon collapsed. Does this ball here have air inside of it? Yes, it does. Oh, it didn't collapse. It got hard like a racquetball and tennis ball. Okay. But what happened to the air inside the ball? Did it still collapse? It had to. Because it got cold, it had to collapse. So now I have a hard, brittle exterior with a collapsed gas or a vacuum inside. What does that make this like? A light bulb. What happens to light bulbs when you hit them? They explode. Reason why that ball exploded, because it is just like a light bulb, has a vacuum inside, has a very brittle shell. When you hit it, it implodes into 1,000 pieces all over the place. So, okay. So we've investigated the material change there. We investigated why we use cryogenics so much. And now, if you have any questions, like I said, feel free to ask them. If not, we will continue on. Do we have any questions right now?
We do have some questions. Can you hear me?
Yes.
So one question, where was it? Allie is asking, what are other uses for liquid nitrogen?
What are the other uses? Well, as I said, the food industry uses it quite a bit. Some chefs use it to enhance flavor by capturing the vapor that is the aroma of the materials and by reconstituting it, recondensing it back into the food. Other places like fish industry, McDonald's, other industries use it for flash freezing because the faster you cool stuff down, the less chance there is for any contamination to build in it. So therefore, they use it for that in the that industry. Machine industry uses cryogenics for treating materials like the aluminum you saw in our demonstration. And it is also used like we do here at Fermilab for cooling. It is actually used as an element to keep our detectors cold, keep the material in our detectors very, very cold, because some cases like the magnet that we showed or the ring, it makes electricity work better and therefore is better for us to operate that way.
And a question related to your demonstration, why do the balloons not crack or fracture at the cryogenic temperatures, but the gloves did?
Actually, the balloons technically do. I am kind of sometimes a little bit careful about how I do this, because as the balloon gets cold, the basic material is reasonably secure if I don't do too much. In other words, it is a little flexible, not too bad. But if I actually sit there and try to, I can actually break the material and therefore it wouldn't reinflate because it's too brittle. It won't stay flexible all the way. It's pretty good. Some balloons are better than others. This balloon is pretty good, so it isn't going to necessarily crack. But a lot of the balloons materials does get a little brittle, and I have had them where they'll crack, so they won't reinflate properly. That's just the way the material is. It is somewhat flexible, but not 100% safe that way.
All right. And then we have two questions that are kind of related. One wanting to know, with the track demonstration, is that the same way to make a hover car? And are there any plans to create transportation using cryogenic train rails 50 or 100 years in the future?
Okay. The hover cars use electromagnetic magnets to repulse and to suspend the cars that are floating. To do it in just driving around, you would have to have metal roads, which isn't very practical to try to consider to operate that way. But as far as whether this is possible in the future, yes. One of the issues is the material that is in this can here, and it's kind of cold, I'll bring it up. The material that's actually in here, this high temperature superconductor isn't very strong in the sense that it can't lift a real large amount of weight. It's enough to lift this little tiny car, but it's not enough to lift a train. But the technology for these high temperature superconductors is increasing very dramatically. And we expect that very shortly, in a few years, possibly 10 years, we will have superconductors that can operate at liquid nitrogen temperature that are strong enough to actually suspend very large loads and therefore possible to use as a magnetic lead system for trains.
And then, well, one more before we move on with the show. How is liquid nitrogen created?
The how liquid nitrogen is actually created is actually the process called adiabatic cooling. That's kind of a big term, but it basically says that anytime a gas expands, it cools down. Now, you might have at home like a propane tank. Well, as the propane in the tank expands, it cools that tank down. And you'll notice that sometimes they have a layer of frost on them because it's cooled down so much as to do that. Well, if you use air, compress it a lot, and then allow it to expand out, it cools down. You take that same air and recompress it and re-expand it, it cools more. You go through that process. The industrial systems that actually do this actually have 3 stages of compression and expansion of the air. And at the end of that sequence, what they're getting out is liquid air. Now, liquid air is oxygen, nitrogen, argon, CO2, and all those different products are then separated out. The reason why nitrogen is so cheap is because what they're really trying to get when they liquefy air is oxygen. Liquid oxygen is much more valuable, but in air, oxygen is only 20% of the air. So you only get 20% of the liquid out that you really want. The nitrogen, it's useful, it's practical. Some companies, some places buy it, but it's not the main product they're trying to produce, and therefore it's not as useful to them. And that's the reason why it's so cheap for us to buy it or other people to buy it for their purposes. So that's the last question right now. So we'll continue. Now, well, actually, if you don't mind, I'm a little thirsty. So if you don't mind, I'm going to have a quick drink of my pop here. Well, you know what? My pop's warm. I don't like warm pop. Oh, wait a second. Oh, I got this. See, you know what I can do? I will just take and put my pop into my liquid nitrogen there. And in just a couple of seconds, what the? Oh, no. Oh. So what happened? Oh, I know what happened. When you freeze pop, what happens is all the carbon dioxide comes out of the liquid, causing the pop to come squirting out of the bottle that way. You ever wonder why the bottle blew up in your freezer the other day? That's what's happening, is the carbon dioxide in the liquid is actually coming out, pressurizing the bottle, causing it to rupture. By the way, is that the reason why they call them fountain drinks? No, probably not. But the reason why that pop came squirting out that way is because it had all the carbon dioxide came out of the liquid, causing it to expand and rush out of the bottle. Now, so I think we're just about ready for this. Now, I usually try to do a cannon, but the cannon is a little hard. So instead of the cannon, I think what we'll use is a barrel. Now, the question, of course, is what do you put in the barrel to see? Well, how about we put lots of ping pong balls? Now, what I'll be doing is I will be taking one of these little plastic bottles. I'll be adding some liquid nitrogen to it, putting the cap on, putting it in my barrel, putting the ping pong balls on top, and watching it explode. Now, if I just did that, it actually takes quite a while for this bottle to build enough pressure to explode. These bottles are actually can withstand a very large amount of pressure. That is the reason why you should never, ever do this at home, because it is extremely dangerous. But I don't want to sit here a long time waiting to see if the bottle's going to blow. So how can I make it go faster? Oh, wait a second. I already showed you. I can use water. As you saw in the Ziploc bag, this water will make the nitrogen boil so much faster that now this bottle will pressurize much quicker. And in that case, it will explode much quicker. Now, normally, if you don't add water, it takes like 3 minutes to develop enough pressure to explode. If I add the water to it, it'll take like 15 seconds. Now, 15 seconds is enough time to put it in and step back. It was so long to wonder if it's actually going to go off, okay? Now when this goes off, it is quite loud. You at home can obviously turn down your sound just a little bit if that was an issue. But in our case, we just have to put our hands over our ears. So I want to be sure that you at home, as we are here, are really ready. So are you ready? I think we are. So like I said, that 15 seconds actually doesn't start until after I put the cap on the bottle, because that's when pressure actually starts building in the container to cause the explosion. So add liquid nitrogen to the bottle. Put the cap on. Put it in my bucket. Add my ping pong balls. Step back. Wow. That was impressive. That bottle really did explode. And I usually like to show you what's left of the bottle afterwards, but I really don't see what's left of it out here anywhere. It's sometimes I don't find them afterwards because they have a tendency to disappear altogether. So I do have one more little quick demonstration, and this is just because it is this time of year. And that is, I have for all of you flowers. Oh, no, I'm sorry. I don't have flowers for all of you. But you all should know what the connection is between these pretty flowers and liquid nitrogen. And it's something about flowers we really like. They smell nice. And if you want to smell this pretty flower, do you take a flower at home and rub it on your cheek? Give you rosy red cheeks. Well, if you started with a red rose, right? But how do you get that pretty flowery smell out of the flower? They do it this way. By cryogenically freezing the flower. All the fragrance gets locked in the petals. Then you can take the flowers out. You can crush the petals and process the fragrance into perfume. That's how lots of perfumes are created, is by cryogenically freezing the flowers or whatever to process the fragrance out. By the way, this flower kind of demonstrates, how cold is it? It's as cold as the guy that would freeze a marshmallow that way. That's how cold this liquid is. So I hope you have enjoyed the show, and I hope you have some more questions. I'll be glad to answer them. And if there's anything you want to see demonstrated, I will be glad to try to demonstrate it along with that.
And we do have some questions. One question was, does my propane gas canister lose gas when left outside during Chicago winters the same way carbon dioxide can escape the soda bottle?
No, in the sense that the container that your propane is in is a sealed container, and therefore it just can't escape. But because it is colder, it doesn't expand as much. The warmer the air is, the warmer the container is, the warmer it is out here, the more the propane will expand, and therefore you'll get more propane out gas-wise to burn. It doesn't change how well it burns, because once it's burning, it's at that temperature. But the amount of gas that actually comes out is less because you have, and therefore you'd have to adjust the thing to get a higher flame because of the lower pressure caused by the colder air around it.
And then another question, I have heard liquid nitrogen can make ice cream. Is that true? How do people work safely in factories that use liquid nitrogen without explosions?
Well, first of all, all of the systems that handle cryogenics have to allow for that gas to expand. That is one of the basic thing that cryogenic engineers and designers have to take into account, is that no matter what type of container you put it in, even these containers, which are vacuum thermoses, are very well insulated. As you see, there's no cold on the outside, even though there's a liquid nitrogen on the inside. They still have to allow for that gas to expand because it will boil and it will expand. And those systems have to be designed to withstand the pressure initially and also allow that extra gas to escape out safely. Now, in industry, like when yes, cryogenics can be used for making ice cream. It is very common, not very common, but reasonably common in the industry to do that. One of the ones in particular, Dipping Dots, actually makes their ice cream particularly that way. That's how they get the little ball shape, is by actually rolling it through a cryogenically cooled funnel. So that's how they actually make it. And one of the advantages of that is when you cool the milk products down that fast, you get what is called microcrystallization. And that means the little crystals that form the ice cream are very, very small. And that makes the ice cream creamier. It actually enhances the flavor and it makes it creamier. The counterexample of that, of course, you leave your ice cream in the freezer for 2 weeks, you look at it, it's got these big crystals on it. Well, that's recrystallization. And that makes the ice cream not taste as good. So that's making ice cream with cryogenics actually makes a nice, creamy, good tasting ice cream. But even when they do that, those industries that use the cryogenics for that have to handle it, have to have the equipment to handle it safely and operate properly.
We have, what would happen if you freeze cardboard?
Cardboard. Well, as you saw, this piece of cardboard was well cold when I was actually using it there, but I can repeat that very easily. I'll take my piece of cardboard. Now, one of the things that most people don't realize, it's just wet. It doesn't really change. It's very cold, but it's just wet. One of the things that most people don't realize is that actually liquid nitrogen isn't that hazardous to your skin. To demonstrate that, now don't do this at home. Of course, if you had liquid nitrogen at home, that'd be kind of interesting anyway. How can I hold it in my hand? I can hold it in my hand because my hand is so hot that it actually is not touching my hand. I can kind of demonstrate that by doing this. What happens when I pour some of this liquid on? It goes running across the stage. The reason why this liquid is running across the stage that way is because it's not actually touching the stage. The stage is too hot for it to touch. Same goes for my hand. My skin is too hot for it to touch. That's the reason why I can actually handle some of the things I handle, because my hand is so warm to it. But the hazard of liquid nitrogen isn't like cardboard. This cloth is wet with nitrogen. If that cloth was against my skin, it'd transfer the cold temperature and give me a burn. I quite often get asked when I do these demonstrations in person, they say, can I try that? You know, and I said, well, the reason I don't is because, see, I know enough that when I do this, not to throw it where I'd get on somebody else or throw it where I'd get it on myself. So the only way I can actually teach everybody how to handle ignition is what? Is if you're naked. No. That wouldn't work either. Because what else on your body absorbs liquid? Your hair. And that is where you could get a bad burn if you threw nitrogen and got it on your hair. Okay, any other questions?
Yes, we actually have quite a few coming through. So one is kind of, they're related. So how long does the pail of nitrogen last before it evaporates? And is the liquid nitrogen in the canisters just evaporating into the air slowly?
Yeah, these containers here will actually hold liquid nitrogen for between 4 and 8 hours, depending on certain other things. So that actually will hold it quite well because they are so good. They're vacuum thermoses, and therefore they don't transfer the temperature real quickly into the liquid. It is boiling in there, but it's boiling very slowly. So it is only slowly coming liquid back into gas and out of the container. Some of these other containers, this container here is a 4-liter Dur, 4LD. Now 4 liters is about a gallon of liquid nitrogen. So that container will actually hold liquid for about a week. That's how good insulation that vacuum insulating layer in there is, and that it doesn't transfer the cold, warm temperature from the outside into the cold gas inside, or cold liquid inside, causing it to boil very fast at all. So yes, it does boil off, but it's very slowly because the containers are so good.
And related to that, can nitrogen be a solid?
Yes, if you cool nitrogen down another 20 degrees, it actually turns into solid. Now, one of the things that's very interesting about solid nitrogen actually is an amorphous crystal. And because of that, it's not stable. So it'll freeze into a solid, but then it kind of shatters. Well, then it refreezes into a solid, and then it'll shatter. So if you actually see a demonstration of solid nitrogen, it's quite dramatic because in the container you have to create the solid nitrogen, it will sit there and continually explode and explode, and it's very entertaining.
And there were some questions that were prompted by talking about liquid oxygen a little bit. How does liquid nitrogen compare to liquid oxygen, and are there uses for liquid oxygen?
Well, like I said, the main reason they're actually liquefy air is to produce the oxygen. First of all, liquid oxygen is a little bit warmer than liquid nitrogen. It's more at -300, -290, as far as the actual temperature of liquid oxygen, the point where liquid oxygen converts into liquid. Another property of liquid oxygen that's kind of unique in that it is a diamagnetic material, which means that liquid oxygen is actually attracted to magnets. So if you have a bowl of liquid oxygen sitting here and you put a magnet, it will actually come up and connect to the magnet because it is magnetic that way. It is very dangerous to use because the oxygen wants to react so much that anything can create a very large explosion or fire. So it's very dangerous to use that way. Now, why they produce liquid oxygen, why they need so much liquid oxygen, there's two main reasons. One is that the steel industry needs it to make steel. Part of the processing for making steel is liquid oxygen is necessary. And so most of the processing plants that actually produce liquid air, convert the air into liquid, are near steel plants. So they can just pipe the oxygen over to the steel plant to make the steel that they need to make. The other area that liquid oxygen is used is almost all hospitals have a liquid oxygen tank outside. That is what supplies the breathing oxygen for the patients. That's because it's not dependent upon electricity. All they need is a dewar out there, and the dewar is going to boil off oxygen at a given rate, and that oxygen can be taken and given pumped into the patients, and so they don't have to sit there and try to create the oxygen out of the air, pure oxygen out of the air, for the patients to breathe. It is the fastest, easiest, safest way for the most hospitals to have breathing oxygen for the patients is having a dewar of liquid oxygen at the hospital.
So I think we have time for a couple more. One question, what would happen if you freeze popcorn?
Oh, popcorn is like the marshmallows. It's very similar. You can add, because it's very light, the marshmallow is very light. That's the reason I can eat it directly from the liquid nitrogen. You can take popcorn, drop it in here, take it out, chew it up. The only thing is, I don't think it tastes as good when it's cold as a marshmallow tastes. I've heard people say that the frozen marshmallow is kind of like a crunchy ice cream taste, which it is, as far as I'm concerned. I agree with them. But popcorn, when it's frozen, it just doesn't taste very good. It's just not as interesting of a taste as compared to frozen marshmallows. But it has the same effect. You will breathe out fog because the popcorn is causing the air in the vapor in your breath to condense out into a liquid.
All right, and last question, favorite part about being Mr. Freeze?
Favorite part about, I get to be inventive in a fun way. Part of this demonstration are things that I've picked up from other people or other demonstrations. I've seen them do it, or I've seen something online doing this or doing that. And other ones are just me trying to come up with a neat idea. The pop was one of those things that I just happened upon. I actually had a warm pop, decided, gee whiz, I want to cool it down, put it in there, and ended up with a big mess and said, hey, that's pretty neat. I should use that in my show because it's pretty neat what happens to pop when you freeze it. And it allows me to be inventive and interesting and creative and try to make a demonstration that is fun and entertaining for all of you. And that's one of the main reasons I have been Mr. Freeze for all the years I've been, is because each time I do a demonstration, I'm thinking about what can I do next time to make it more interesting, different, or better. So, and I really appreciate Fermilab's allowing me to be Mr. Freeze, allowing me as a part of my job to go out and do these demonstrations. And I'm really looking forward to being able to get back to doing live demonstrations for schools and libraries and such. So.
Well, thank you so much. This is wonderful. Thank you for giving up time, everyone, on your Saturday and joining us to see Ask an Engineer, A World Without Atmosphere, tomorrow at 1 o'clock Central. Thank you so much again for joining us, and we will see you at future open house events.
Thank you.